Looking under the hood, you can see the O2 sensor at the back of the engine bay. This is the upstream sensor. And then off to the side, you can also see the connector for said O2 sensor. Then taking a look under the vehicle, you can see the downstream O2 sensor placed in the catalytic converter. The downstream sensor is also a traditional zirconium narrowband sensor. Looking at our wiring diagram, you can see that both sensors share a common power wire, and you can see that our downstream sensor has 4 wires going into it, and then the upstream wideband sensor has 6 wires going into it. This sensor is also a ion pump style wideband sensor. Another thing to take note of is the heater circuits for both sensors. You can see that they will have power whenever the key is on, and they are PWM controlled through the ground side, through the PCM. In terms of testing with our downstream sensor, we can test voltage output to see if it's reading rich and lean correctly, and then we can also test the heater circuit resistance to make sure it's at the correct value. And then with our wideband sensor, we can really only test the resistance of the heater circuit. With the O2 sensor at room temperature, we were seeing 3.5 ohms of resistance on the heater circuit. Then from there, we started the car up to see how the resistance would change when the sensor was hot. We got the sensor up to 260 degrees, and the resistance in the heater circuit changed from 3.5 to 4.6 ohms of resistance. Because we unplugged our sensor, we caused a P0030 DTC code, and the ECM wasn't seeing the voltages it was expecting to see. Looking at our lambda PID for our upstream sensor, you can see that it's running slightly rich. This is because we're injecting propane into the intake to cause it to run rich or read rich. And then as we also then let off the propane eventually, you'll see that it will steady back out. Next, we're going to be taking a look at the PIDs on my 2000 540i. On the 540i, the O2 sensors are located under the vehicle, just before the catalytic converter and just after the catalytic converter. Looking at the diagram, you can see that every sensor is a 4-wire sensor, and there is one common wire that runs to all 4 of them, that being the power for the heater circuit. You can also see that there's shielding wrapped around the wires that's then grounded to help protect the signals coming from the sensors. These O2 sensors are also the other style of wideband sensor, that being a critical current sensor. While I'm not certain on this fact because there was very limited information, I believe that even the downstream sensors are also wideband sensors. Part of the reason I believe this as well is because there is 4 PIDs I can look at for lambda values. Taking a look at our lambda values, you can see that there's 4 of them, 1 for each sensor. I was not able to find which was which, but it is possible to watch them go rich or lean as I rev the engine.
Now we are going to be taking a look at the oxygen sensors on my 2020 Ford Explorer ST.
Looking at component location here on the Ford Explorer, if you were to face the front of the vehicle, on the left hand side we have our upstream oxygen sensor mounted before the catalytic converter. Down here we have our downstream oxygen sensor mounted in the middle of the catalytic converter. On the right hand side, same thing, we have our oxygen sensor mounted before the catalytic converter, and then our second oxygen sensor mounted in the middle of the catalytic converter. Since the number 1 cylinder is on the left hand side of the engine, that would be bank number 1. So here we have oxygen sensor 1-1. Down here we have oxygen sensor 1-2, and on the right hand side that would be bank number 2. So here we have oxygen sensor 2-1. Then down here we have oxygen sensor 2-2. Here, taking a look at our wiring diagram, you can see that we have 4 heated oxygen sensors. Starting down here with our upstream sensors, here we have bank 1, sensor 1, and at pin 76 we have our heater control, which is a green and brown wire, and leaves the sensor through a green and orange wire. At pin 14 we have our measured pumping current in a green wire. At pin 29 we have our pumping current in a brown and yellow wire. At pin 44, we have our voltage reference wire. And at pin 59, we have this first or unique wire that Ford does not have an exact description of, but we can see that it is yellow and green. You can also see here that pin 14, 29, 44, and 59 are both twisted pairs. You can see here as well, that's a shielded wire. Down here as well, pin 46 is our heater control, which is a gray and violet wire that leaves the sensor through a green wire. Then here we have our measured pumping current, a brown and blue wire at pin 15. And then pin 30, we have our pumping current, which is a white wire. Pin 45 is our voltage reference, which is a violet and green wire. And then here we have our first or unique wire again at pin 60, which is white and green. Coming up to our downstream sensors, here at pin 84, we have our signal return, which is a white and orange wire, which comes into a connector from the PCM to a white and red wire. At pin 10, we have our signal from the PCM as a yellow and green wire into a connector into the sensor. At pin 77, we have a white and orange wire, that is our heater control, which comes from the PCM and leaves in a green wire. At pin 16, we have a blue and white wire as our heater control into a connector, goes through the sensor and leaves through a green wire. At pin 26, we have our heater signal circuit, which is a white wire, goes into the sensor, leaves through a green and white wire from the sensor to a connector and into a green wire back to the PCM.
Taking a look at our scan tool data that we have pulled up, we have our bank 1, oxygen sensor 1 and 2 pulled up for reference. We can see our current lambda value, our actual air to fuel ratio, and the voltage that the sensor is seeing. So when we take a look at the lambda value, we can see that it takes several spikes and dips. When the lambda value dips below 1, that indicates a rich mixture in the air-fuel ratio, and when the lambda value is above 1, that indicates a lean mixture. Taking a look at the actual air-to-fuel ratio on the right-hand side, we can see that when the throttle is pressed, the air-to-fuel ratio drops down, but when the throttle is let off, the air-to-fuel ratio spikes incredibly high up to a lean mixture. The highest we saw was about 29.3. And then looking at the downstream oxygen sensor, it likes to keep a voltage around 0.45 volts for the stoichiometric ratio. So when it dips below that number, it indicates a lean mixture, and when it is above that number, it indicates a rich mixture.